Put this in recording. Alright, so in the last class we were talking about the structure of the molecule. I told you this kind of the molecule are called tetrahedral, where you have a central atom. You have a central atom here, and then two are going. One is coming toward you like this, and then two are here, and one is going like this, away from the board, right? So let's say this is H, this is H, this is H, this is H, and you hold like this, and this is this one, and this is trying to penetrate and going away the board, and this is coming toward us. So this one. So this is called tetrahedral molecule, and this is 109.5 degree bond angle, but in paper we really write like this. In paper we write like this, but this is not the true structure. This is the true structure. This is called tetrahedral molecule, and tetrahedral bond angle is 109.5 degree. So that's what I told you. And I showed a lot of other molecular structure. And in one, I told you that let's say you have a molecule like this, and if this is the water molecule, this is the oxygen, this is hydrogen, hydrogen. If there are no electron, no free electron, that is, this is a lone pair. If there are no lone pair, it looks like this linear molecule. Its bond angle is 180 degree, 180 degree, and it's like a straight line. But in water molecule, the oxygen has 4 lone pair electron like this, and this lone pair repel each other. Lone pair and bond pair repel each other. Bond pair and bond pair repel each other, and this is pushing it down. And water molecule is not a linear like this, and it is like this, like the V shape. Yeah, so this is very important. If there are a lone pair in the central atom, this is always bent structure. And I give another example. Ammonia. So this is ammonia. So let's say if ammonia has ammonia NH3. So if there are no dot in the nitrogen here, if there are no dot here, the lone pair electron, this would look like the planar structure. The planar structure is like, it would look like this, right? It would look like this, all in the same plane. So this is hydrogen, this is hydrogen, this is hydrogen, this is nitrogen. So they all are in the same plane. But since nitrogen has a 2 lone pair here, they push these bonds, and the nitrogen is really a pyramidal structure. Pyramidal structure, and bond angle is about 107 degree. Yeah?
Oh, sorry. I just have my phone here.
Sure. That's okay.
Sorry?
Yeah, so this looks like this. So I will put this kind of material in exam. Is ammonia planar or pyramidal? Is water a bent structure, or it is a linear structure? Yeah, something like this. And then another one is, so let's say boron trifluoride. So we have a boron here, and then I have fluorine here, I have fluorine here, I have fluorine here. So these are kind of the exam question, yeah? And then let's say it doesn't have a lone pair here. Since BF3 in B there are no lone pair, so it looks like this. All are in the same plane. So this in the board, this in the board, this in the board, right? But if there were a lone pair here, what the structure would look like this. Structure would look like this. Yeah, if there is a lone pair. But since this doesn't have a lone pair in boron here, it looks like in the same plane. If there were a lone pair, it would bend like this, down. Yeah, so this is an important concept. Now let's go to slide number. So we talk a lot of structure there in the last class. Now in the same file, let's go to the slide number 15. So I think this is in the lecture 3, continuation from the last class. So here is a structure. So let's say this is a sulfur here at center, and we have chlorine here, and we have chlorine here, like this. Sulfur dichloride. So its name is sulfur dichloride. And we have 1, 2, 3, 4 dots there. There's a lone pair, right? So what is this structure of this molecule? It is a linear like this. Is it linear like this? or it is bent like this. So this is a right structure or this is a right structure, right? That's what we are talking. So since there are two lone pair here, the lone pair push the bone pair too much, so this push this down, they push it down, so the structure look like this. This is the structure. So SCl2 is a bent structure because the sulfur atom at center has lone pair, so the lone pair push this bone pair with great force and bend the structure. Make sense? So if you see any dot or any lone pair at the central atom, immediately you should say, oh, it is a bent, it's not a linear. If there are three, it is a pyramidal, it's not a like that. Now, so this was a slide number 15. Now let's talk about the slide number 16, the new concept. This is a new concept. So we have not discussed so far this concept, electronegativity. 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 So electronegativity is to make a molecule. Let's say you have a water molecule like this, right? So this is a water molecule, HOH, H2, right? Now there is one bond here. So this is the 2 electron. In one bond is 2 electron. This one bond is 2 electron. So which atom in this structure attract more toward it? So these are, let's say this is a hydrogen. If this hydrogen attract this shared pair of electron with great force, we call this as a higher electronegativity. Yeah. But if this oxygen has more force to pull this shared pair of electron toward it, we call oxygen has more electronegativity. Yeah. So electronegativity is a characteristics of a atom in a molecule by which it try to attract the shared pair of electron toward itself. So if these electrons are attracted more toward oxygen, oxygen has a greater electronegativity, and the electron would sit near oxygen but not near hydrogen, like this. Yeah. So electronegativity is basically for the shared pair of the electron in that bond. So oxygen has more electronegativity. So this electron, the bond electron, don't sit exactly in the middle. They sit more toward oxygen, like this. And hydrogen here has a less electronegativity, and oxygen has more electronegativity. So these two electrons here are attracted more toward the oxygen, like this. Yeah. Make sense? So if you write the charge here, we give this slightly negative charge, and this one slightly positive charge, slightly positive charge. This comes from the electronegativity difference. Why slightly negative? Because electrons are more attracted toward oxygen, and electron has a negative charge, so oxygen has slightly negative charge. And hydrogen, electrons are shift more toward oxygen, so we give hydrogen slightly positive charge. Here also, these two electrons slightly shifted toward oxygen, so we give the slightly positive charge. So if you look previously in, I think, lab number 4, we were drawing the water like this, and we are giving D minus here, and D plus here, and D plus here. Make sense? So it's like this. Why charge developed in a water molecule or some other molecule? Because of the electronegativity difference. One atom attracts the shared pair of the electron with a great force toward it. Yeah? And another cannot attract with that much force. Good? So this is how the polarity develops in the molecule. So let's write some electronegativity value here. So I have lithium here, beryllium here. So lithium has a 1 electronegativity value. Do I have hydrogen? Yeah, I have hydrogen also. I'm going to write here hydrogen. Hydrogen has electronegativity value of 2.2. So this guy has 2.2 electronegativity. So the force by which the hydrogen attracts the shared pair of electron is 2.2. Yeah, and lithium has 1. Lithium has electronegativity value 1. Sodium has 0.9. So if you look here, the electronegativity value decreasing going from top to bottom in a group. Yeah, and go to this way. Hydrogen here is a beryllium. Beryllium has a 1.6. So 1.6, and look, boron. The boron is 2.0. Carbon is 2.5, and nitrogen 3, oxygen is 3.5, and fluorine is 4. So if you look here, the electronegativity value decreases as we go from top to bottom in a group, because their size become too big, and when the size is big, they cannot attract the electron easily. Yeah. If you go to right from the in the periodic in the period from left to right, electronegativity value increases. So lithium has 1, beryllium has 1.6, boron 2, carbon 2.5, nitrogen 3, oxygen 3.5, fluorine 4. So electronegativity value increases as we go across the period. Why? Because the size becomes small due to the effective nuclear charge. Yeah. So we talked those concepts in previous class. As you go from left to right, size becomes smaller, so they can attract the electron with great force. Yeah. So these are the electronegativity value of some of the elements. Now let's go to the slide number 17. So if there are two atoms sitting together, and if the electronegativity difference is 0, is a completely, let's say, En difference. So electronegativity difference. Difference. So electro NCE, and the polarity. We talk here polarity. So what is the relations between the electronegativity difference and polarity? So if the electronegativity difference between the two atoms is 0, it's completely covalent, right? So let's say electronegativity difference is 0. Electronegativity difference is 0. Let's say two hydrogen are making a bond. This is a hydrogen, this is a hydrogen. So this is a hydrogen molecule. So what is the electronegativity of this one? 2.2. And what is this one? 2.2. 2.2 minus 2.2 is 0. So in S2, the electronegativity difference between two hydrogen atoms is 0. So this H2 molecule is completely covalent, no polarity. Completely covalent, there is no polarity, no plus sign here, no minus sign here. So both is 0. Make sense? Now, a difference of electronegativity between 0.1 and 0.3 indicates that the bond is non-polar covalent. So if the electronegativity difference is from 0.1 to 0.3, this is also non-polar. This is non-polar. It's just like this one. This is covalent. This is also kind of covalent, non-polar. So let's look something here. 1.8. So it's okay. So if you subtract from this number to this number, and you get either 0.1, 0.2, 0.29, or 0.3, that's also non-polar. Yeah, non-polar. Now, a difference of 0.42, we'll practice this one. A difference of 0.42, 1.7 indicates that this bond is polar covalent bond. So we need to write the charge, D plus and D minus. And if we have a electronegativity difference of 1.8 or more, it is ionic bond. It is ionic bond. So we practice a couple of these things, and then we are good. So let's practice a couple of problems here. How about H and S? So I have one example there, H and S. This is a hydrogen molecule. So what is the electronegativity difference between these two atoms? 2.2, and this hydrogen is a 2.2. 2.2 is 0. So electronegativity difference is 0 here. So 0 means this bond is completely covalent bond. Yeah, covalent bond. Now let's talk another one here, HF. So HF, this is a hydrogen fluoride molecule. What is the electronegativity of hydrogen? 2.2. And what is the electronegativity of fluorine? 4. So 4 minus 2.2 is 1.8. So the difference is 1.8. So it falls to, is it 1.8? No. How much is that? 4 minus 2.2 is, yeah, 1.8. Yeah. So it's a little bit, it's greater than 1.8. Actually, more than, not 1.8 or more. It's more than 1.8. More than 1.8. More than 1.8. So So it's a 0.4 to 1.8 is pretty much, this is a polar covalent bond. So maybe you may write something here. So 0.4 to the 1.8 is polar covalent bond. So when we write the HF molecule, we give a D plus here, D minus here. This is the polar. Yeah, just that 1.7, just to make 1.8 there. 0.4 to 1.8 is polar. More than 1.8 is ionic. Yeah. So change that 1.7 to 1.8. Good. Now another one is LIF. Let's draw the LIF here. So this is a Li, this is F. So this bond is polar or non-polar or ionic. So let's calculate the electronegativity difference. What is the lithium? It's a 1, right? This is 1. And then fluorine is 4. So this is 4. So 4 minus 1 is 3. So more than 1.8 is ionic bond. So LIF is completely ionic. So if you put in water, the LIF, the Li goes one way, F goes another way. They break and they fly away. Make sense? So like this one. Now, do I have other here? So let's do another in 19, slide number 19. So let's do slide number 19. So it's slide number 19. So in slide number 19, we are calculating which is the most polar, HF, CF, HF, CF, and OF. So we have these 3 bonds here, 3 molecules, 3 kind of bond here. So one is HF bond, another is CNF bonding, another is ONFR bonding. So which one is most polar? So let's calculate the electronegativity difference. So hydrogen is 2.2 here. If we calculate here, this is 2.2, and the fluorine is 4. 4 minus 2.2 is 1.8. So the electronegativity difference here is 1.8. Let's calculate this one. C is 2.5, fluorine is 3. So fluorine is 4. So 4 minus 2.5 is 1.5, right? 1.5. So let's calculate OF. So O is 3.5, 5, F is 4. So 3.5 minus 4 is 0.5, right? So look the maximum electronegativity difference. So this is the very large electronegativity difference. So this is the most polar. Make sense? So this is the most polar. This is the least polar. So this is like the covalent. This is like the 1.8 is like the polar. And how about this one? Also 1.5 is between 0.4 to 1.8. So this is also polar. So if we write this molecule, we give D plus here, D minus here, because this has bigger electronegativity value. Yeah? And then how about here? 0.5. So 0.1 to 0.3 is non-polar, but more than 0.3 is polar. So this is also polar. So this is D minus, this is D plus. But if you put in water, which is the most soluble in water? This is the most soluble in water, because this is a highly polar, because the electronegativity difference is 1.8. This is a little bit less soluble in water, because this is a little bit less polar. And this is the least polar, so this dissolves in water, but it doesn't dissolve as much as HF. So that's what it is saying. So HF is the highly polar, CF is a little bit less polar, and OF is the least polar. Yeah. So this is on the polarity. Now, so this is the polarity. So is the bond polar or non-polar? We can just find by this this chart, right? Now let's talk about the molecular polarity. Molecular polarity. So this is that. So I'm going to talk about the molecular polarity. So if you see the bonds are polar, and look how the atoms are rearranged there. So this is oxygen, this is hydrogen, this is hydrogen. So is this molecule polar or not, right? That's what we want to find. So this is asymmetrically distributed. So if this both hydrogen are turning toward the ground like this, you see that? So this is oxygen, hydrogen is turning toward ground, hydrogen is turning toward the ground, right? And there are also some electrons here. So this is not symmetrically, they are pointing toward one way, right? So if something is pointing toward only one way, if there is no symmetry, they are polar. So this is a polar molecule. Make sense? So, but if this was like this, so let's say this molecule is like this. So hydrogen, this is oxygen, this is hydrogen here, and this is one oxygen, one electron maybe the other way, other electron is like this way. If it was like this, it would be non-polar, because it would have something like this. So let's see if I have here. So like this, it would look like this, right? Make sense? So the one or two electron would go like that, two electron coming like this, and then it's completely symmetrical. It would be completely symmetrical, and it is not like it is not the polar. Make sense? So if look around the molecule, if things are symmetrically distributed, the molecule is non-polar. If the things are unsymmetrically distributed, they are polar. So it's like that. So let's say here is a seat. Let's say here is one seat, and here is one seat, and there are two galls here. Let's say these are galls. So two galls, and there are also two galls. So this is a non-polar, because two galls are sitting in two sides of the seat symmetrically, right? But if one gall is sitting this way and two galls are sitting this way, then this becomes the polar immediately. Make sense? It's a polarity. Or let's say you have a seesaw. Let's say you have a seesaw like this. This is a seesaw, and here is a 70 kg man sitting here, and here is a 30 kg man sitting here. This is a polar, because things are not symmetrically distributed. Because if 70 kg man sit here, it just goes down and this goes up, right? So this is a polar. Make sense? But if this is a 30 kg and this is also a 30 kg here, both are same, exactly same, 30 kg, then this system is a symmetrical and it's non-polar. Make sense? So it's not polarized. So this is polar. So water is polar. Why water is polar? Because both hydrogen are turning toward down and oxygen are pointing away. So this is unsymmetrical and this is polar. Now let's look at this one. This one. So this is a CH4, right? CH4. This center is C and this is CH4. So this is also symmetrically. They are all distributed, these things, equally in all sides, right? This is CH4 is this one, C. So this is C, and H here, another H is here, and one H is turning away from the board, another H is coming toward us. So this is also symmetrical, because four things are pointed equally in all directions. Make sense? So this is non-polar. CH4 is non-polar. 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 Now let's see CH. What do I have here? BF3. Let's look this molecule BF3. The F. You see here that these three things are sitting. All these three things here are same. In center there is B, and here is a F, here is a F, and here is a F. So balanced. They are very, very, very balanced, and since they are equally distributed, very uniformly in all sides, this is non-polar molecule. Make sense? BF3 is non-polar. So if you put it here, it looks like this, non-polar. It's not bending this way, it's not bending this way, it's not bending this way. So they are all same thing, sitting in the same plane and balancing. Yeah? So this is non-polar. So if this molecule was like this, if you have the molecule like this, this is non-polar. This is polar. Why this is polar? Because all three are pointing down, right? So that would be polar. But since they are not doing that, so they are just doing like this, then this is non-polar. So all balanced. This is not going this way, this is not going this way, this is not coming this way. So all are distributed equally, evenly. So this is a non-polar molecule. Now let's look this one. Is this molecule polar or non-polar? You see here, this is center atom is something like the sulfur. Maybe this is a sulfur, and you have the big blue thing here, big blue thing here, and here are some other color things are here. So this is unsymmetrical distribution. Make sense? This is not so. So this way, there are two different colors. There are two different colors. So they are the things around this central atom are not distributed equally. So this is polar. Make sense? So don't think too much and look around the central atom and how the things are distributed. If the things are distributed equally, that's non-polar. If the things are distributed unequally, that's a polar. Yeah. So let's look another one here, Cl2CO, something like that. So let's look Cl2CO. So at the center we have C, and here is O, and here is Cl, and here is Cl. Are things distributed equally here? No, right? So big here, double bond here, and chlorine here, things are not distributed equally. So this is a polar. It's a polarization. Make sense? Now, how about another one? We have ammonia. So we have ammonia. Ammonia is like this. So ammonia is like this. You see here. So this C is going toward Earth. This C is also going toward Earth. This C is also going toward Earth, right? Like this down. But there is nothing going like up here. So they are not balancing each other, right? So all are polarized because these three things are all pointing downward. So this is also polar. Make sense? Good. So ammonia. So ammonia look like this. So ammonia N is here. One hydrogen is going down. Another is also going down. Another is also going down. Maybe there are 2 electrons here. So this must be polar because all 3 hydrogen are pointing down. Yeah, polar. But if this ammonia was like this, N and one H here, another H here, another H here, all in the same plane like this, all in the same plane like this. It will be non-polar. Make sense? So this is BF3, BR3, BBR3, BBR4, whatever. This kind, they look like this, and they are non-polar because things are distributed equally around the central atom. But in nitrogen, things are not equally distributed, like this. So 1, 2, 3, all are distributed toward the ground, and this electron is pointing off. So this is polar. Make sense? Good. So this ammonia is polar. So what do I have here? So Cl2CO, BF3, so we just did it. Now let's look other thing here, CH4. Now I already show you CH4, so things are equally distributed around the C. This is this way, this is this way, this is this way. So if you put this in the air, so you look all sides and they look the same, right? Symmetrically distributed. So this is non-polar. Now in the CH4 is non-polar. Now let's put CH3Cl. So CH3Cl. So I put one here, different one. So let's say this is a Cl here. Now like this. Now like this. You see here CH3Cl. So this way, 3 are pointing this way. One different is pointing this way, right? So this is definitely polar. Make sense? So CH3Cl is polar. So if you write the structure here, so C, so you can hold like this, or you can hold like this. It doesn't matter. So you put the this green thing here. So this is going like this way, and this one is here. This one is this thing is here. This blue one, and this is coming toward us like this. Yeah. So this is like this. You see, the things are not symmetrically distributed, right? See, this is 2 big atoms here. So these 3 are pointing like this. If you look here, these 3 are pointing toward you, and this pink is pointing toward me. Or you can hold like this. This pink is pointing toward you, and these 3 green are pointing toward me. So there is no symmetrical distribution of the atom around. So this is a polar. Make sense? Good. So this is polar. Now let's look another one. We have CS2Cl2. Now CS2Cl2. So I put this one here, and I put it here like this. CH2Cl2. It looks like this. It looks like this. CH2Cl2. Can you see it? This is C. This is 2S. This green are S. This pink are Cl. So this pink are turning toward you, and then this green are going away like this. So this is polar. It's not symmetrically distributed. Make sense? So this is not symmetrically distributed, so this is polar. Now how about CHCl3? Now let's do CHCl3. Now it's becoming more polar. So let's say here CHCl3, so Cl3 is like this. If you hear CHCl3, now this S is coming toward you, right? And then Cl are pointing away. So this is also unsymmetrical distribution, right? Or you can hold like this, and this 1, 2, 3 are coming toward you, and this green thing H is going away. So this is also unsymmetrical distribution. Make sense? So this is also polar. Good? So polar. Now let's look the last one, CCl4. Now CCl4. Do I have another one here? So CCl4. So CCl4 is like this. Now look here, all look same, symmetrically distributed, right? All sides, same thing. Yeah? So coming toward you also, same thing, going away from you also same thing, pointing up is same thing, pointing down is same thing. No matter how you hold it, all things are distributed equally in all directions, right? So this is non-polar. Make sense? So this is non-polar. When you have something like this is non-polar. None. So this one and this one will be going away from you. This one and this one are coming toward you. So if you hold like this, so these two things, this one and this one, same thing, coming toward you, and then this one and this one are going away from you. And so this is the most symmetrical distribution in tetrahedral structure, and this is a non-polar. Make sense? So I will put some problem about the polarity. Good. Now what do we have here? So we are done here. So I'm going to start another slide there. So we have, I posted another set of slides. That's a lecture 4 in Canvas. So I'm going to start that one. So let's say that's slide number 1. So this is, I'm in the lecture number 4, and I'm in slide number 1. So we don't study this kind of thing in our class. So if you go to the organic chemistry class, you will study more about this one. So the structure, the molecule look like this. So if you make the structure, so let's make one structure like this. So here is H, and there are double bond, and there is a single bond, there is single bond C, and there are, so things looks like this. So sometimes there are 2 bonds between the atoms, and there is single bond between the atom, and sometimes there are 3 bonds between the atoms. Yeah, like that. So I think this is not O. This is N. This is N here. Yeah, N like this. So this is called double bond. So this is called double bond. There are 4 electrons between 4 electrons shared between 2 atoms. So this is double bond. So this is single bond, single bond, single bond, and this is triple bond. There are no 4 bond in chemical compound, only up to 3. So single bond, double bond, and triple bond. So we call bond order. So what is the bond order of this one? Single bond is given as bond order is 1. Bond order 1. What is the bond order of double bond? We give bond order as 2. What is the bond order of this bond? The bond order is 3. We call bond order. So number of bond is called bond order. If there is 1 bond, we call bond order is 1. If there are 2 bond, we call bond order is 2. If there are 3 bond, we call bond order is 3. There is no 4 bond order or 0 bond order in chemistry. Yeah. So the maximum number of bond we can have is only 3. Good. So like this. And let's look another here. So maybe I don't need this one. Now let's look at another one, fractional bond order. We already talked in the resonance structure. If you make a structure like this is nitrogen and this is oxygen here. Is it in central atom? There is no. All right, so nitrogen and here is oxygen, like this. So sometimes there is a double bond here. In another structure, it has a structure like this, and single bond here and double bond here. So neither this is the real structure nor this is the real structure. So the real structure is like this, and single bond here, O, and you put dot here, dot here. So this electron from this double bond are distributing like this. So this is called resonance structure. If you remember the resonance structure we call in the previous class. So if there is a central atom and both atoms are same atom in both sides, and there is a double bond, this double bond electron, these two electrons here don't sit in one seat here. So sometimes they move this way, sometimes they move this way. So these are distributed over these three atoms like this. Yeah. So like this. So they put like this. So meaning that these two electrons are just moving this way, this way, this way, this way, like that. And they give this is neither a single bond, nor a double bond. So this is kind of 1.5 bond. 1.5. Yeah, bond order is 1.5. So if you have a resonance structure, meaning that there is a central atom and both atoms in either side are the same, oxygen, oxygen, or something else, and there is a double bond somewhere here. This double bond doesn't sit like that way. This double bond electron just distribute over all these three atoms like this. Yeah, so this is called the 1.5 bond order. Good. So here you may say, oh, this is the bond order is 1. You may say the bond order is 2. You may say here bond order is 1. Here bond order is 2. But in real life, in NO2, neither there is a double bond nor there is a single bond. The bond, when scientists go to the laboratory and measure the bond length of this NOO, they both sides they find 1.5, 1.5. So that's the resonance structure. Yeah. 57. This is called the fractional bond order because it's a 1.5 bond. Now let's talk about the bond length in slide number 3. I am in the slide number 3 from the lecture 4. So bond length. What is the bond length? We already talked about this bond length in previous class. So let's say this is one atom, this is another atom. So let's say this is a H2, right? H and H. So this is a one hydrogen atom, this is another hydrogen atom. So the distance between the center of these two atoms is called bond length. Make sense? So what is the bond length? So we have hydrogen in hydrogen. So what they do is they measure the distance between the two atoms, and that is called the bond length. So like this. So I might have to write a little bit better way. So they just touch here, hydrogen and hydrogen just touch here, and you take the distance between the center of these two atoms, and this is the bond length. Make sense? So what is bond length? The bond length is the distance between the center of the bonding atom. Yeah? Good. And so this is like this. So if you look another one, chlorine looks even bigger, like this. Chlorine is bigger. So when the atom are bigger, the bond length is bigger, because we are measuring the distance between the center of two atoms. So if you say this is a carbon, this is a carbon and carbon, the distance between carbon and carbon center is 154 picometer, this distance. But since chlorine are very big, the distance between two chlorine atom is 198 picometer, center to center. And if you look the carbon and chlorine, so this carbon is small, chlorine is bigger, and the distance between carbon and chlorine is 176. 176. When the atom are bigger, the bond length is bigger. Make sense? When the atom are smaller, bond length is smaller. So let's say this is a small atom, this is another small atom. So the bond length between them is very small. As the size of the atom increases, the bond length increases. So it's basically same thing in the slide number 4. HF bond is small, HCl bond is bigger, and HI bond is very big. Why? So go to the slide number 4 and look there. So fluorine is this small, and then this is hydrogen. This is hydrogen. This is fluorine. So both are small. So this is the distance between them is small. But if you look the hydrogen and chlorine, so this is hydrogen and chlorine is pretty big like this, and the distance between this in this center is big. This is chlorine. This is hydrogen. When the size of the atom increases, the bond length increases. Now look the hydrogen iodide. So this is hydrogen, and this is iodine is even bigger, and the distance between this one and this one is very large. So hydrogen iodide bond is very big, very long. HCl bond is a little shorter. HF bond is very short, and if you measure the H and H bond, maybe even smaller. I don't know. Maybe it's smaller there. Yeah. So what I'm trying to say is that smaller the size of the atom, the smaller is the length of the bond. Yeah. Good. So that is like that. Now let's look another one here. Slide number 5. These are pretty easy concepts. So now bond length. Let's say here is something like this. So if I am going to do in a single one here, so let's say like this here, and maybe O here, double bond here. Maybe I put H here. Maybe 1, 2, 3, 4. So it's everything is good here. So let's look here. So this is a bond order 3, right? This is a bond order 2. This is a bond order 1. So if you see here, the single bond is very long. Yeah, very long. Single bond very long. Single bond is very long, very long. So double bond is a little bit shorter than single bond, shorter than single bond. And this bond, the triple bond, is shortest length. Make sense? So if there are a triple bond, this bond is very short. Yeah. If there is a single bond, it's very long. And if there is a double bond is shorter than single bond, longer than double bond, like this. Yeah. So I just draw in scale. So this is a very short here. This is a little bit longer than that one. This is a very long. Make sense? So that's what I'm writing in the next slide in number 5. Slide number 5. Yeah. Good. So if you see the single bond, it's the longest. If you see the double bond, it's a little bit shorter. But if you see the triple bond, this is the shortest bond. So let's look here. I have here something like this. So yeah, I have C here, and this is C, and I have OH here, and I have H here like this. So if you look this CC bond, here is a 1.41. This CC bond is 1.41 single bond. 1.41 I think angstrom. Yeah, 1.410 angstrom. And if you look the double bond like this, the bond length is 1.31. So this is 1.31 angstrom. Now if you look the triple bond, so if C is here and 1, 2, 3 here, so the bond length is 1.19. Make sense? So this is the longest. 1.41 is the longest. 1.31 is in between. 1.19 is the shortest. So third, if there are 3 bond, shortest bond. If there are 2 bond, longer than triple bond. If there is a single bond, the longest bond. Yeah. Now, if we want to break the bond, To break this bond is easy. Single bond is just a single. It's easy to break the single bond. It has the smallest bond energy. The to break the double bond is little bit harder. So it has more bond energy. And to break the triple bond, it is even harder. So it has the highest amount of the bond energy. Make sense? So in the next slide, I am talking that one. So let's write down. So what is the bond energy? So let's look the slide number 6, and I have this here. See, double bond O here, single bond H here, O here, and I have something like this. Now, if you look the bond energy to break this hydrogen bond, I just need 414 kilojoule of energy. But to break this CO bond, I need 754 kilojoule of energy. Why too high energy is needed to break this C double bond O? Because there are double bond. To break the two string take more force, right? And then to break this single bond, we just need a small amount of energy, almost double. So it's about 800, it's about 400. So single bond is about 400, double bond is about 800. So if there are a triple bond, even bigger energy is needed to break that bond. Yeah? So if you have something like this, a small amount of energy is needed to break this one. If you have something like this, more amount of energy is needed to break this bond. If you have something like this, even more energy is needed to break this triple bond. So we just finished the slide number 6. Now let's go to the slide number 7. Yeah, so I just taught it. Maybe if I cannot finish this one, I will finish this in next class, and we start at chapter 9, and that's the last chapter. Yeah. So what is the bond strength? So bond strength is measured in terms of the bond enthalpy. If you did the lab number 11 in the laboratory last week, what is bond enthalpy mean? You already know enthalpy. Enthalpy means how much heat is needed to break it bond, or if the bond is formed, how much heat it gives out, right? So that is called a bond enthalpy. So bond strength. So how strong is the bond is measured as the bond enthalpy. Bond enthalpy. So what is the bond enthalpy? So bond enthalpy is like this. So C and C. So how much heat energy is, how much energy we need to give to break this bond? That energy is called bond enthalpy, and that measures the bond strength. If a large amount of energy is needed to break this bond, that is high bond enthalpy, and that's a very strong bond. Make sense? So if you look the bond enthalpy, see this is a C triple bond, C double bond. So to break this bond, we need a small amount of energy. So bond enthalpy is small, bond strength is small. Two bonds here, we need to break two bonds here, so we need to give a lot of energy from outside to break it. So bond enthalpy is high, so very strong bond. Now this one, there are three bonds. So if you want to break this bond, you need to give a lot of energy to break three bonds. So this has the highest bond enthalpy, and this is the strongest bond. Yeah, same thing. We are just repeating the same thing for different concept. So let's look here. So they call bond enthalpy. Sometimes they call bond dissociation energy also. So just you have to dissociate this bond, and how much energy you give to break that bond is called bond dissociation energy. So let's look some example here. So here is a chlorine gas. So I have 1 minute time. Chlorine gas, chlorine. Here, Cl is bond here. This is a gaseous, and then how much energy you need to break this bond and give two chlorine atoms? So you need to give 242 kilojoule of heat energy. So put in this beaker, put 6.023 10 to the power 23 molecules of chlorine, and give 242 kilojoule heat energy here, and all chlorine gas atom is broken down to chlorine atoms. Yeah, so that's it. So thank you very much, everyone. So we are just in time. So I have a couple of slides, and I will finish this on next class, and we start chapter number 9. It's very right time. very exact time we are finishing all chapters. Yeah, I'm going to stop it. Thank you very much.